Thank you, everybody. Thank you, everybody. So my name's Mark from Newcastle University, from the Microsystems Research Group in the UK. I'm doing a part-time PhD after over 25 years in the rainfall measurement industry. So basically what I'm going to be talking about today is the problems with rainfall measurement, mostly known as undercatch, which is basically an estimation of rainfall, and how I'm trying to combat that with instrumentation. So the overview of what I'm going to talk about today is there's going to be an introduction and motivation, then there'll be some background work that we've done, then there'll be the design of the laser-based analyzer, this paper, and then the experimental method and results, followed by the conclusion and future work. So rainfall measurement provides historic and near real-time data for Met services and hydrologists. These are used for modelling and for water balance calculations and for forecasters. So it's very important that these are correct. Current methods suffer from well-known rainfall undercatch. This is predominantly caused by wind, although there is other things that do cause their errors. But as you can see from this table, which is taken from a paper from 1953, that basically the exposure to wind can be anything from 5% to 80% errors in rainfall measurements. So this is why I'm concentrating solely on the wind effect, because the other errors just don't come anywhere near what the problem is with wind. So just to visualize what I'm talking about here is rainfall traditionally is caught in rain gauges, and we have a surface area of a gauge here, and when the wind blows across the gauge, it causes turbulence in the top of the gauge, which then extracts rain that would have normally fallen in there, and therefore it is not measured. So good gauge design and calibration and correct sighting can minimize these errors, but it will never eliminate them. The fact that you've got an object here is going to cause some errors. So some basic principles, because I presume there's not very many rainfall experts in the audience today. This is what a typical rain gauge looks like, and what you have to remember is you're not measuring the rain that you catch at this area, it's what represents at the ground area. So what goes in the top of the funnel here is a representation of what you would have hit the ground. And then inside the instrument, it's normally you have a tipping bucket or weighing mechanism to actually measure the precipitation, the water content. And then therefore you can convert, you know the surface area, you know how much water you've got, you know the volume of the bucket, you can therefore calculate the rainfall in millimeters or inches. So that's the basic principle. The background of the work that we've done over the last 25 years is in the late 90s and early 2000s, we did over 10 years of research into best gauge shape design. And this is the shape that was come up with that was the best. It's a combination of how high this area is, so you don't get outsplash of the rainfall as it falls into the gauge. But then you've also got to have the aerodynamic shape to push the wind underneath the catching area. So you reduce the amount of wind that goes across the top. So this is the design we came up with. In 2015 to 2018, I was an industrial supervisor for a PhD student who carried out a lot of comparison field work between standard straight-sided gauges and the aerodynamic gauges, and also used what is known as a World Met Organization reference pit, where basically the gauges are placed out of the wind at the ground, and this gridded is to break up the turbulence of the wind as it flows across the top of the gauge. So this is what we call the reference. This is what we say is the ground truth, literally. And then it's going to compare with the rest of the gauges we have here. So the results were, as you would expect, basically that the pit gauge, the two pit gauges caught the most rain. This is from a storm event back in 2015 it was, in July. The next one was basically from the ground mounted aerodynamic gauges that caught the next amount of rainfall the best. And then it was basically the pedestal mounted gauges that caught the next. And finally, it was the straight sided gauges. So we also, at the same time, during this industrial PhD, we worked with the University of Genoa in Italy, who runs the World Met Office Precipitation Centre. They carried out some CFD analysis on the shapes of gauges. And this is the gauge that we use down here for our tests. You can see instantly that this chimney-shaped type gauge causes turbulence across the top here. So when rainfall is coming in, it gets blown away, a lot more gets blown away. Here, you've got much more smooth turbulence outline here with the analysis, which therefore means it's probably a lot easier for us to do some correction algorithms in the future. Some key points to take away from this research is we tried to correct for just using wind data alone for the undercatch and rainfall measurements, but there proved to be something else missing. So what we thought this must be to do with is the actual size of the drops, the raindrops that are coming into the gauge must have an effect on it, and the drop distribution. This is where my work begins. So here we get to the laser-based analyzer that's been added to an ordinary type gauge that we use, the ordinary aerodynamic gauge. So what we have here is we have a dual laser beam that goes across the top of the orifice of the gauge, so the raindrops coming in here cut through the laser beam. It's produced here with a laser, and the next one should show you better in the test setup. We have the laser here, and then we have a Fresnel lens for focusing the beam. It then goes through a 50-50 beam splitter, which then produces the bottom beam, and then the top beam is produced by a mirror, which goes across here. On the detection side, we have 6 photodiodes in two arrays, so 12 in total, detecting the beam. And basically, when the raindrop goes through, then you get a drop in voltage. Then the electronics it goes through is it's a very simple transimpedance amplifier, which then goes into a differential amplifier. But what we did notice, we were getting a lot of noise on the system. So we realized it was from the ambient light. So what we did is we added a third photodiode array, but we pointed this one vertically upwards and ran that through the differential amplifier. So this basically cuts out and allows to compensate for the ambient light. So the experimental method that we used it's very difficult to get permission to actually put rain in a laboratory. So we basically purchased a lot of glass spheres from the varying sizes from 1 millimeter to 10 millimeters. And we used those to initially test this system by dropping them from a known height through the system. And we recorded what was coming out of the photodiode array on a picoscope. And we did that over 100 times with different combinations and different sizes. This is an example of one of the picoscope samples that we did. This was dropping a 5 mil, 6 mil, and another 6 mil. So 3 simulated raindrops are being dropped through the beams here. You can see the 2 beams we have here. That shows, and we've got basically the 3 drops coming through here. How much the voltage decreases by gives us an idea of the diameter of the drop. So this is the 5 millimeter, this is the 6 millimeter, and this is the 6 millimeter going through the beam. We know the distance between the 2 beams on the system, which is 25 millimeters. We can therefore, when it crosses through the 2 beams, we get an indication of this t time, which gives us a bonus piece of data, which is the velocity of the raindrop entering into the gauge. So then we feed this into a neural network. This is the data gathering section that I've just explained here before. So the 100 sampled waveforms are then put through the system to produce a CSV file of the data. Then we put it through the train validate. What we did is for this neural network, we split it into 40, 40, 20. So that we trained with 40% of the data, and we basically tested with the 20% at the end. So what we also used, we used 2 neural networks here, a classification neural network to determine the number of raindrops, and a regression neural network to estimate the raindrop size. So these were the initial results. What you have to remember from this is we're not looking for perfection here. We're basically looking for an indication of how big the raindrop is to feed into an algorithm. So this is not a scientific piece of data that will be basically used for meteorological purposes. This is literally just to say during that storm, the average drop size was what it was, and we can then feed that into the algorithm along with the quantity of rainfall that's been, and also you'll see later we're going to add ultrasonic wind sensors to the gauge, which will give us the wind speed at the time. So onto the conclusions and future work. We managed to create a laser-based analyzer, which is detailed in this paper, effectively detecting and measuring raindrop size and distribution. With this addition to a standard rain gauge, it will now be possible to collect data, not just volumetric rainfall catch, but also the size of drops and distribution, vital for more accurate rainfall measurements. And then we can use that next year, in the next year's work, in this new wind correction algorithm. So the future work that I'm now working on now is to add additional ultrasonic wind sensors to the gauge, which is now just being completed. I'm now busy writing that up. And then basically we're going to do a field test campaign similar to the one we did in 2015. But this will be with all of those gauges that you saw there, with the reference pick gauge, but also with this new prototype. Well, several of these new prototypes. We'll also investigate methods using neural networks to calculate multiple simultaneous drops, because at the moment we've only tested up to 3. And then we're going to be developing an embedded system. At the moment, this is being run on Python on a PC level. We now need to basically get it onto an embedded system level, and then we'll be using machine learning like TinyML, etc., with focusing on speed, low memory usage, and energy efficiency. Thank you very much.